Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi Herman and Corin. So we were chatting about some of the pretty fundamental stuff in computers recently. We mentioned CPU architecture is the difference between 64-bit, 32-bit, AMD 64, Raspberry stuff that'll run on a Raspberry Pi. And the other one I wanted to chat about was the differences between the main file system types. We've talked about the exotic stuff that I'm actually have become really fond of. Through the power of Claude Code, I was able to install BTRFS, and those systems, BTRFS, ZFS, XFS, are works of art in computer science terms. I use BTRFS because it has snapshotting at the OS level. That is basically my main pain point in Linux, is occasionally breaking stuff, and being able to know that I can occasionally, as a fallback, just roll back the file system was enough for me to want to use it. So BTRFS is a great one. But the more classic ones are ext4, FAT32, and then there's like a long list when you go into one of those, partition formatting tools and you choose which file system type you want. You think that that's it, and then there's like a drop down with 20 or 30 weird and wonderful ones that I always wondered, what are those? But let's talk about the big ones, Herman and Corin, FAT32 versus ext4. They bring up compatibility challenges between different operating systems, and I always wondered, we're getting very low here to the binary. We're talking about the block level rather than data. So how fundamental is the difference between these different types, and which is the dominant one? Are we going to get one that'll kind of reduce the friction between the worlds of Linux and Windows and just work across platforms? Because I've always just used, before I went to BTRFS, I just always opted for ext4, unless there was something that needed FAT32, because I use Linux. But it would be nice to know that something, if I created a USB drive or something, that anyone could stick it in their computer, or that my operating system could be easily ported. Herman and Corin, let us chat about these differences between file systems, and what is that big list of all these strange and obscure types that we see in those menus sometimes.
Hey everyone, welcome back to My Weird Prompts. I am Corin, and I have to say, I am feeling particularly organized today. Maybe it is because we are finally diving into a topic that is literally the foundation of how we organize our digital lives. It is February 20th, 2026, and while we are all living in this world of massive cloud buckets and AI-generated content, the actual physical way that data sits on a piece of silicon or a spinning platter still matters immensely.
And I am Herman Poppleberry, the man who has probably spent more time staring at partition tables and hex dumps than is strictly healthy for a human being. Honestly, Corn, I've been looking forward to this one since we started the show. It is one of those topics that sits right under the surface of everything we do, but most people only think about it when they get that dreaded drive not recognized error, or when they are trying to recover photos from a corrupted SD card.
Exactly. It is like the plumbing of your house. You do not care how the pipes are laid out or what material they are made of, until there is a leak in the basement or the water pressure drops to a trickle. Today's prompt comes from Daniel, and it is a deep dive into the plumbing of our data. He is asking about the differences between file system types, from the modern heavy hitters like BTRFS and ZFS to the classics like ext4 and FAT32. He even wants to know about those obscure ones you see in the drop-down menus of partition tools, and specifically, what is happening at the block level.
It is a fantastic prompt because it hits on so many different levels. There is the practical side, like what works between Windows and Linux, and then there is the deep, technical, block-level stuff that explains why certain file systems are better at protecting your data than others. We are talking about the difference between just storing data and actually ensuring its survival over decades.
Right. And Daniel mentioned he has been getting into BTRFS and ZFS lately, which are definitely the flashy modern options that people talk about in the home lab and Linux communities. But before we get into the high-end stuff, let us set the stage. For anyone listening who might be a bit fuzzy on the concept, what is a file system really? At its most basic level, what is it doing?
Think of your hard drive or your SSD as a massive empty warehouse. It is just billions of tiny little cubbyholes, which we call sectors or blocks, where you can store a bit of data. If you just started throwing data in there without a system, you would never find anything again. You would just have a pile of bits. The file system is the librarian, the map, and the inventory management system all in one. It decides how files are named, how they are stored, and how the operating system can find them again.
So it is the index. But it is more than just a list of names, right? It handles the actual physical arrangement on the disk.
Precisely. It manages things like fragmentation, which is when a file is split across different parts of the warehouse. It handles permissions, which is deciding who is allowed to enter which cubbyhole. And it handles what we call metadata, which is the data about your data. That includes things like when a file was created, when it was last modified, and what type of file it is. And as Daniel pointed out, at the block level, these systems can look very different. A block is usually a 4 kilobyte chunk of space. The file system has to decide which blocks belong to which file and in what order.
Let us start with the classics. Daniel mentioned FAT32 and ext4. FAT32 feels like the universal language of storage, even though it is incredibly old at this point. I feel like every thumb drive I've ever bought comes formatted as FAT32. Why is it still everywhere in 2026?
FAT stands for File Allocation Table. It was developed by Microsoft in the late 70s and 80s. FAT32 specifically came out with Windows 95 OSR2. The reason it is still everywhere is simplicity. It is the lowest common denominator. Because the specification is so simple and has been around for so long, almost every operating system on the planet, from your smart TV to your digital camera to your Linux server to your microwave, knows how to read and write to FAT32. It requires very little memory and very little processing power to manage.
But it has some pretty massive limitations, right? I remember trying to move a high-definition movie file to a thumb drive a few years ago and getting an error even though the drive was mostly empty.
That is the infamous 4 gigabyte limit. Because of the way the file allocation table is structured, using 32-bit integers to address clusters, an individual file cannot be larger than 4 gigabytes minus 1 byte. In the 90s, a 4 gigabyte file was unthinkable. Today, a single 4K video file or a modern video game can easily dwarf that. It also lacks a lot of the safety features we take for granted now, like journaling.
Explain journaling for us. That feels like a key concept when we talk about the difference between something like FAT32 and the more modern systems.
Journaling is basically a safety log. Imagine you are writing a long letter and you have a notebook where you first write down, "I am about to write page 5." Then you write page 5. Once you are done, you check it off in the notebook. If the power goes out while you are writing, you can look at the notebook and see that page 5 was never finished. You can then discard the messy, half-written version and keep the rest of the letter intact. Without journaling, if the power cuts out while the computer is writing a file, the file system can end up in an inconsistent state. You might get what we call a corrupted file system, where the librarian thinks a file is in one place, but the data is actually halfway somewhere else.
So ext4, which is the standard for most Linux distributions, is a journaled file system. How does that change the game compared to the old FAT systems?
ext4, or the fourth extended file system, is incredibly robust. It is the evolution of a design that goes back to the early 90s. It handles much larger files, up to 16 terabytes, and volumes up to 1 exabyte. But its real strength is its reliability. It uses that journal to make sure that even if your computer crashes, the file system itself stays healthy. It is also very efficient at preventing fragmentation. Unlike Windows' old NTFS or FAT systems, you rarely need to defragment a Linux drive running ext4 because it is smart about where it places data blocks to begin with. It uses something called extents, which allows it to map a long range of contiguous blocks with a single index entry, rather than listing every single block one by one.
Okay, so if ext4 is so good and reliable, why are people like Daniel moving toward things like BTRFS and ZFS? What is the next level that those systems are reaching for?
This is where it gets really exciting, Corn. We are moving from traditional file systems into what I like to call the era of storage management systems. BTRFS and ZFS are not just file systems, they are also volume managers.
Meaning they handle the physical drives as well as the files?
Exactly. Traditionally, if you wanted to combine multiple hard drives into one big pool, you would use something called RAID, or Redundant Array of Independent Disks. That usually happened at a hardware level or a separate software layer like LVM in Linux. But BTRFS and ZFS bake that right in. They understand the relationship between the physical blocks on the disk and the logical files. This allows them to do things that ext4 simply cannot do.
Daniel mentioned he loves BTRFS because of the snapshotting. He said it is his main pain point in Linux, breaking things and being able to roll back. How does a snapshot work at the block level? Is it just making a copy of everything?
No, and that is the magic of it. If it were just making a copy, it would take forever and use up all your space. Instead, these systems use something called copy on write, or COW.
I love that acronym. Tell me more about the cow.
Think of it this way. In a traditional file system like ext4, if you want to change a word in a document, the system finds the block of data where that word is stored and overwrites it with the new word. In a copy on write system, it never overwrites anything. Instead, it writes the new version of the data to a brand new empty block. Then it just updates the file's metadata to point to the new block instead of the old one.
So, the old block is still sitting there?
Exactly. It is still there, untouched. A snapshot is essentially just a saved version of those pointers. It says, remember where all the blocks were at 10 o'clock this morning. Even if you change every file on the system, the old blocks from 10 o'clock are still there until you tell the system to delete the snapshot. This makes snapshots nearly instantaneous and incredibly space efficient. You only use extra space for the changes you make. This is why BTRFS has become the default for distributions like Fedora and OpenSUCs. It gives users a literal time machine for their operating system.
That explains why Daniel can just roll back his entire operating system if he breaks something. He is just telling the system to look at the old pointers again. But what about ZFS? People talk about ZFS like it is the gold standard for data integrity.
ZFS takes this even further. It was originally developed by Sun Microsystems for Solaris, and it is often called the last word in file systems. ZFS uses something called Merkle trees. Every single block of data in ZFS has a checksum, which is like a digital fingerprint. These fingerprints are stored in the parent block all the way up to the root of the file system. Every time the system reads a block, it calculates the fingerprint and compares it to the one stored in the parent.
And if they do not match?
Then ZFS knows the data has been corrupted. This protects against something called bit rot, or silent data corruption. This can happen because of a failing hard drive, a loose cable, or even a cosmic ray hitting a memory chip. Yes, that actually happens. If you have a mirrored setup or a RAID Z setup in ZFS, it does not just tell you the data is bad. It uses the good copy to automatically repair the corrupted one without you ever knowing there was a problem. It is self-healing storage.
That sounds like the ultimate peace of mind for data hoarders. But I have heard ZFS is a bit of a resource hog. Is that still true in 2026?
It is definitely more demanding than ext4. ZFS loves RAM. It uses it for something called the Adaptive Replacement Cache, or ARC. It tries to keep as much data as possible in memory to speed things up. A general rule of thumb used to be 1 gigabyte of RAM for every terabyte of storage, though that is a bit of an oversimplification now. For a home user with 16 or 32 gigabytes of RAM, it is perfectly fine. But you would not want to run it on a low-power Raspberry Pi with only 1 gigabyte of memory.
What about XFS? Daniel mentioned that one too. It seems to be the middle ground or something.
XFS is an interesting beast. It was originally developed by Silicon Graphics back in the 90s for their high-end workstations. Its specialty is performance, especially with very large files and high-throughput environments. It is a 64-bit journaled file system that is excellent at parallel input and output. It divides the drive into different allocation groups, which allows multiple processors to write to the drive simultaneously without stepping on each other's toes.
So it is the heavy lifter for big enterprise stuff.
Exactly. It is the default file system for Red Hat Enterprise Linux for a reason. It is incredibly stable and scales to massive sizes. While it does not have the same built-in RAID and snapshot features as BTRFS or ZFS by default, it has recently gained something called reflink support. This allows it to do some of those copy-on-write tricks, like instant file cloning, which makes it much more competitive for modern workloads.
Now, let us address that long list of obscure types Daniel mentioned. When you open a tool like gparted or the Windows Disk Management tool, you see all these weird acronyms. Things like F2FS, JFS, RiserFS, and even things like HFS+. What are we looking at there?
A lot of those are historical artifacts or very specialized tools. Let us take F2FS for instance. That stands for Flash Friendly File System. It was designed by Samsung specifically for modern flash memory like SSDs, SD cards, and NVMe drives. Traditional file systems like ext4 were designed for spinning rust, hard drives with physical platters and moving heads. F2FS understands the way flash memory works at the physical level. It knows that flash memory has a limited number of write cycles and that it has to be erased in large blocks. F2FS tries to write data in a way that minimizes wear and tear, which can significantly extend the life of an SD card in something like a Raspberry Pi or an Android phone.
Interesting. So if I am formatting an SD card for a project, F2FS might actually be a better choice than the standard ext4.
In many cases, yes, especially if that project involves a lot of writing to the disk. Then you have things like JFS, which was IBM's journaled file system. It was one of the first to bring journaling to the world back in the OS/2 days, but it has mostly been eclipsed by ext4 and XFS in the Linux world. It is still there for compatibility, but you rarely see it used for new installs.
And what about RiserFS? I feel like I remember that being a big deal in the early 2000s. It was supposed to be the next big thing.
It was. RiserFS was very innovative. It was incredibly fast at handling lots of tiny files, which is something most file systems struggle with because of the overhead of creating new inodes for every tiny file. However, its development stalled for some pretty dark reasons involving its creator, Hans Reiser, who was convicted of murder in 2008. Because of that, the community support dried up. There was a Reiser 4 project that tried to keep the torch burning, but it never made it into the main Linux kernel. Most modern Linux distributions have officially deprecated it.
Then there are the Apple ones, HFS Plus and the newer APFS.
Right. Apple used HFS Plus for decades. It was fine, but it was getting very long in the tooth and struggled with things like modern SSD speeds and massive file counts. APFS, or Apple File System, is their modern replacement that rolled out around 2017. It is actually very similar to BTRFS in some ways. It uses copy-on-write, it supports snapshots, and it is highly optimized for the solid-state drives that Apple puts in all their Macs and iPhones now. It also handles encryption much more gracefully than the old systems.
It is funny how all these different companies and communities eventually converged on similar ideas, like journaling and copy-on-write, because they realized those were the only ways to handle the massive amounts of data we have now.
It is a classic case of convergent evolution in software. As drives got bigger and CPUs got faster, the bottlenecks shifted. We stopped worrying about the CPU overhead of a complex file system and started worrying about the reliability of the data itself. But this brings us to one of Daniel's most practical questions. Which one is the most dominant, and is there one that works seamlessly across platforms like Linux and Windows to reduce friction?
This is the holy grail, isn't it? Being able to plug a drive into any machine and have it just work without thinking about it. No drivers, no command line tweaks, just plug and play.
It really is. In terms of sheer dominance, if you're talking about the world of desktop computers, NTFS is still the king because of the massive install base of Windows. NTFS, or New Technology File System, was a huge leap forward when it arrived with Windows NT. It brought journaling and advanced permissions to the Windows world long before the average consumer had it. If we are talking about the internet and servers, ext4 and XFS are the rulers of the kingdom. And if you're talking about mobile phones, most Android phones actually use ext4 or F2FS internally, while iPhones use APFS.
But none of those play well together. You cannot just take an ext4 drive from a Linux machine and plug it into a Windows box and expect it to show up in File Explorer. Windows will just tell you the drive is unformatted and ask if you want to wipe it.
Exactly. Windows still does not have native built-in support for ext4, which is honestly a bit ridiculous in 2026. You can use WSL2, the Windows subsystem for Linux, to mount those drives, but it is not a seamless experience for the average user. Similarly, while Linux can read and write to NTFS now, thanks to the NTFS3G driver and the newer kernel-level NTFS3 driver from Paragon Software, it is not always perfectly smooth, especially with permissions and fast startup hibernation files from Windows.
So for that frictionless cross-platform experience Daniel is asking about, what is the answer? Is it still FAT32?
No, for most people, the answer is exFAT.
exFAT. That is the successor to FAT32, right?
Yes, it stands for Extended File Allocation Table. Microsoft released it in 2006 specifically to address the limitations of FAT32 while keeping the simplicity. It removes that 4 GB file size limit. It can handle files up to 16 exabytes, and it can handle massive drives. Because Microsoft eventually opened up the specification and joined the Open Invention Network, it is now supported natively in Windows, macOS, and Linux.
So if I'm making a portable drive for backups or moving files between my laptop and my desktop, exFAT is the winner?
For a portable drive, yes. It is the closest thing we have to a universal language. But, and this is a big but, Corn, it does not have journaling.
Ah, so we are back to the safety issue.
Precisely. If you are using an exFAT drive and you pull it out of the USB port without ejecting it properly while it is writing, you have a much higher risk of corrupting the whole thing compared to an NTFS or ext4 drive. It is a trade-off. You get universal compatibility, but you lose that extra layer of safety. If you are moving a 500 gigabyte video project, you really want to make sure you click that eject button.
That seems to be the recurring theme here. Every file system is a set of trade-offs between compatibility, performance, and data integrity. There is no such thing as a perfect file system.
It really is. Even something as advanced as ZFS has its downsides. For example, ZFS is very memory hungry, as we discussed. It also historically made it difficult to expand a storage pool. If you had a RAID Z array of 4 drives, you couldn't just plug in a 5th drive and expand the capacity easily. You had to add a whole new group of drives. Now, as of 2024 and 2025, the OpenZFS project has finally stabilized RAID Z expansion, which is a huge deal, but it took nearly 20 years to get that feature right.
I want to go back to the block level question Daniel had. He asked what the fundamental differences are at that level. We talked about copy on write, but what about how they actually track where a file is? I have heard the term enode used a lot in Linux circles. What is an enode, and how does it differ from what Windows does?
An inode, or index node, is a data structure that describes a file system object like a file or a directory. Think of it as the librarian's card in the old card catalog. The enode does not store the file's name. That is actually stored in the directory entry, but it stores everything else. It tells the system which blocks on the physical disk belong to that file, who owns it, what the permissions are, and where the data starts.
So when I move a file from one folder to another on the same drive, the data is not actually moving?
Correct. On a system like ext4, moving a file is just taking that inode and pointing a different directory entry at it. The blocks on the disk stay exactly where they are. This is why moving a 10 gigabyte file within the same partition is instant, but moving it to a different drive takes forever. You have to actually copy the blocks and create new inodes on the destination drive.
That makes so much sense. Now what about FAT32? It doesn't use inodes, does it?
No, FAT32 uses a much simpler system. It literally has a table, the file allocation table, that lists every cluster on the drive. For each cluster, it either says this cluster is empty, or it points to the next cluster in the chain for a specific file. It is like a giant game of connect the dots. To find a file, the system starts at the first cluster and follows the chain until it hits an end-of-file marker.
That sounds inefficient.
It is, especially as the drive gets full and the files get fragmented. If the dots for your file are scattered all over the warehouse, the librarian has to run back and forth across the building to collect them all. That is why defragmenting was such a big deal back in the day. It was the process of rearranging the blocks so the dots were all in a straight line, making it faster for the physical hard drive head to read them. On an SSD, fragmentation matters much less because there is no physical head to move, but the overhead of a messy file system can still slow things down.
Modern systems like BTRFS and XFS are much better at avoiding that in the first place, right?
Much better. They use more advanced structures like B-trees to manage their data. Instead of a simple list or a chain, they use a hierarchical tree structure. This makes searching for a specific block of data incredibly fast, even on massive drives with millions of files. It is the difference between looking through a phone book page by page and using a high-speed search engine.
So, looking at the landscape today, if someone is setting up a new Linux machine like Daniel, why would they choose BTRFS over the tried and true ext4? Is it just for the snapshots?
Snapshots are the headline feature, but there is more. BTRFS also supports transparent compression. It can compress your files on the fly as they are written to the disk and decompress them when you read them. This saves space and can actually improve performance because the computer is spending less time waiting for the physical drive to move data, even if it has to use a bit of CPU power to do the compression. In 2026, our CPUs are so fast that the compression overhead is basically zero.
That is clever. It is using the extra power of modern processors to make up for the slower speed of storage.
Exactly. It also has built-in support for multiple drives, allowing you to easily add more storage to your system without having to reformat everything. It is very flexible. However, it is still considered slightly less mature than ext4. There have been some historical issues with its RAID 5 and 6 implementations, though those are mostly resolved now. If you want absolute, rock-solid stability where nothing ever goes wrong, ext4 is still the king. If you want modern features and a safety net, BTRFS is the way to go.
And what about the new kid on the block? I have been hearing people talk about BCachefs lately. Where does that fit in?
BCachefs is the rising star. It started as a cache layer for the Linux kernel but evolved into a full-blown file system. It aims to provide the features of ZFS and BTRFS like snapshots, compression, and multi-drive support, but with the performance of XFS and the code cleanliness of ext4. It was merged into the Linux kernel in late 2023 and has been gaining a lot of traction. Some people think it will eventually replace BTRFS as the preferred modern Linux file system because its architecture is much cleaner and easier to maintain.
It feels like we are in this transition period where the old ways are still dominant because of momentum, but these new features are becoming essential as our data becomes more valuable and our drives get bigger. When you have a 20 terabyte drive, a simple file system error can be catastrophic.
Definitely. When you are managing that much data, you need those checksums. You need to know that the photo you saved 5 years ago hasn't had a single bit flip from a 0 to a 1. Without a checksumming file system like ZFS or BTRFS, you have no way of knowing if your data is actually intact until you try to open it and the file is corrupted.
So, to wrap back to Daniel's question about friction. If he wants a system that works across Windows and Linux, he is looking at exFAT for portability. But what if he wants to mount his Linux internal drive in Windows?
That is the tough one. There is a project called WinBTRFS, which is a third-party driver that allows Windows to read and write BTRFS drives natively. It is actually surprisingly good, but it is still a third-party driver. If you are doing professional work, you might be hesitant to trust your data to it. Most people in 2026 are using WSL2 to bridge that gap. You can actually pass a physical disk through to the Linux subsystem in Windows, and then Windows can access the files through a network share interface. It is a bit of a workaround, but it is the most reliable way to do it without risking corruption.
I have to say, Herman, you've made the librarian of the hard drive sound a lot more exciting than I expected. It is really a battle of logic and safety happening at the nanosecond level. It is about how we trust these machines to remember things for us.
It really is. Every time you save a photo of your kids or download a podcast, there is this incredibly complex dance happening between the software and the physical hardware, all managed by these file systems. It is one of the great unsung triumphs of computer science. We have gone from simple tables in the 70s to self-healing multi-drive, compressed, and snapshotted systems today.
Well, I think we have covered the map of the warehouse pretty well. We have looked at the old guard like FAT32 and EXT4, the modern titans like ZFS and BTRFS, and the specialized tools like F2FS and XFS. Before we head out, I want to give a quick shout out to our listeners. We have been doing this for over 700 episodes now, and the community you all have built around my weird prompts is just incredible.
It really is. We love seeing the discussions in the contact forums and hearing how you are using these deep dives in your own projects. Whether you are building a massive ZFS storage server in your basement or just trying to get an old SD card to work with your retro gaming console, we love being a part of that journey.
Yeah, it makes a huge difference. And remember, you can find all our past episodes, our category taxonomy, and a contact form at myweirdprompts.com. We also have an RSS feed there for those of you who like to keep things old school and decentralized. Maybe you are running your own RSS aggregator on an ext4 partition right now.
Or if you want to reach us directly, you can always shoot an email to show@myweirdprompts.com. We love hearing your thoughts, your corrections, and your own weird prompts. Daniel, thanks again for this one. It was a great excuse to let me nerd out on block-level storage for a while.
Guilty as charged. It was a blast. This has been My Weird Prompts. I am Corn.
And I am Herman Poppleberry.
Thanks for listening, and we will catch you in the next one. Goodbye.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.